All right, so let's get back into it. We've talked a little bit about sort of the machinery we use to breathe, both in and out, and also the muscles we use to basically change the volume of our lungs or our thoracic cage, such that we can change air pressure that would enable air to flow into and out of our lungs. I want to talk a little bit about the dynamics of this system. And by that I mean, what dynamics mean is how does a system change as it changes. Some of this is a little bit contingent on exactly where you are when you're breathing in and out. So we've talked already about the sort of equilibrium point of thorax and lung volume. Technically speaking, you can call that the resting expiratory level. How does the dynamics, or how does the mechanics of the system change as you move away from that resting expiratory level? At volumes above that resting expiratory level, the lungs will contract due to relaxation pressure alone. We've talked about that as well. So you breathe in actively, and then you just kind of let go, and you go back down to the sort of equilibrium point. You can, if you want to, get actively involved to make that happen a little more quickly, but you don't have to. When you're below the resting expiratory level, the opposite happens, right? The lungs will tend to expand due to relaxation pressure. To continue expiration at this level, active expiration would be necessary, so you'd have to keep pushing. What would happen if you keep pushing is kind of the answer eventually the question we want to look at here to see how the dynamics work is what would happen if you go through sort of the entire extent of your lung capacity from the biggest point to the smallest, and trying to breathe out at sort of a constant level or a constant flow of air as you're doing that. Before we get into that, I'll walk you through some more technical terms. Normally I write these all out on the board. So if you want to write these down or take a note of them as we go, just feel free to do so. As it is, I'm just going to talk you through them. So the total lung capacity is the volume of air you have in your lungs after a maximum inspiration, as much as you can fit in there. I think that is fairly straightforward. Total lung capacity. The residual volume is what's at the opposite end of that. So the amount of air that remains in your lungs after a maximum expiration, the amount of volume in your lungs in this system that you basically can't get rid of. Thirdly is the vital capacity, which is the difference between these two. So basically the whole range of volume you have in your lungs between the total lung capacity and the residual volume. You can technically define that as the greatest amount of air that can be expelled from the lungs after a maximum inspiration. And if you remember at the beginning of the previous half of this lecture, this is what we tried to do at the very start. Maximally breathe in and then maximally breathe out. So go from your total lung capacity to your residual volume. You span the entire vital capacity when you do that. Another useful volume concept is the functional residual capacity, which is the volume of air contained in your lungs at the resting expiratory level. So when you're at equilibrium, that's how much volume you have in your lungs. And you can also define the inspiratory capacity based on this concept. So the inspiratory capacity is the maximum volume of air that can be inspired from the resting expiratory level. So if you happen to just be temporarily at peace and then breathe in as far as you can go, you go all the way from your functional residual capacity to your total lung capacity. That range is going to be called your inspiratory capacity. And I'm mentioning these because these diagrams I'm going to show you next will make use of these sort of landmarks in terms of your total lung volume. There's some kids screaming in the park across the street, presumably having fun. I will just ignore them as we go. Okay, so this is the equilibrium point of the lungs and thorax. You can see abbreviations of some of these concepts that I've mentioned here on the side. The one going from 0 to as far down as you can sort of pull the spring is called the total lung capacity. At the shortest end, we have the residual volume, and I'll point out here, I think I kind of mentioned this before, but if you left the lungs by themselves, they would be only this big. The smallest you can make them when they're connected up to the rib cage is here, so that's still bigger than they would be on their own, but obviously it's going to be smaller than we get at equilibrium. This is the residual volume. This is the total lung capacity. The difference between those two is what we're going to call the vital capacity. Like, what's the range of your breathing volume, basically. I pointed this out before. This is our equilibrium point. It's called the functional residual capacity. And then going from there to the total lung capacity is your inspiratory capacity. How much can you breathe in from equilibrium point? Something which is kind of interesting to note is that this difference, which we don't have a term for, but equilibrium to the smallest point in volume, or the smallest amount of volume you can have in the system, is only 35% of your vital capacity. So this is smaller than this. You can breathe in more than you can breathe out when you're at equilibrium. How about that? Okay, yeah, and so maybe this is the system trying to take, one of the things about this sort of relaxation pressure phenomenon where you can sort of breathe out without having to put any effort into it is, number one, people want to be lazy. Another way to think about that, as I normally like to say, is that people like to be efficient, or biological systems like to be lazy/efficient, so they can get the most bang for their buck when they're trying to put effort into something. So if you don't have to put an effort into something, why not put effort into it? Because, it's hard to find energy out there, or at least it used to be before this whole civilization thing happened. Anyways, so the reason I was talking about that is that it gives you kind of more room here for inspiration than you get for expiration. So, and since we're getting sort of the default expiration for free, why not get more of that for free than less of it? Okay, so here's this example I was going to walk you through. When you produce speech, you generally want to have a more or less continuous flow of air coming out from your lungs. If you have a continuous flow of air, that's going to require constant alveolar pressure in your lungs, at least compared to the air pressure outside of your body. So if you wind up pushing your system to the extremes, this becomes tricky, and this is the dynamics of the system I was referring to before. Because at the extremes, you get more relaxation pressure, both high and low, of lung capacity. Sort of in the middle, if you don't push it too far, you get this sort of nice linear relationship, but at the far high end and the low end, it becomes more of an exponential sort of increase or decrease in relaxation pressure. And I'll show you some graphs to kind of substantiate what I just said there here in a second. So when you are sort of pushing things past the equilibrium, you have to dynamically compensate with active inspiratory and expiratory forces if you want to keep things constant, if you want to have a constant alveolar pressure in your lungs to provide a continuous flow of air coming out of your mouth. Okay, so this is the relatively complicated graph, which kind of shows you how this works, and I'll try to walk you through it. So this is air pressure here on the x-axis, and the external air pressure is plotted here in the middle, this straight up and down solid line. And let's say we're going to do this little thought experiment where we're going to try to breathe out with a constant flow of air. So like breathe all the way in, and then try to say something like ah at a very constant level of intensity and flow of air throughout until you get to the very bottom of your lung capacity. I'm not going to do the whole thing because that would take quite a long time, actually, it turns out. But hopefully you get the picture. If I'm breathing out at a constant rate and maybe phonating on top of that, I need to keep my alveolar pressure constant as well. So the difference between the alveolar pressure and the external air pressure is going to be the same as we go from our max vital capacity here to our min vital capacity. So I'm going to breathe all the way in and then start to breathe out with constantly until we go all the way down to the bottom until we don't have any more air left in our lungs. Okay, so what happens is that the other curve plotted on this graph is this one here through the middle, which is relaxation pressure. So if I push my lungs, if I make them bigger than the equilibrium, there's going to be a relaxation pressure to go back down to the equilibrium, right? I get that for free just to because of the way these two things are linked up with each other. So here's the equilibrium point. Like I said, it's about 35% of your vital capacity. And if I expand my lungs beyond that, then I get this relaxation pressure. It increases here. And at the start, as I increase the size of my lungs, this relaxation pressure is increasing linearly. But then when I get to the very extremes of my system, this is why I had you try to get to the extreme of your system at the start of this lecture. When I get to the extreme of this system, that pressure starts to increase exponentially. It takes a lot more effort basically to get to the extreme of the system once you're at the edge than it does to kind of float through the middle here. So if I have the most amount of air I can get into my lungs, the highest possible amount of air I can get in there, the relaxation pressure is actually going to increase quite a bit at 100%. So what I want to do, what I want my alveolar pressure to be is here, but my relaxation pressure is actually a lot more than that. So my lungs kind of naturally want to breathe out a lot more intensely than I'm trying to target with this weird example where I'm trying to breathe out at a constant rate all the way from the most amount of air in my lungs to the least amount of air in my lungs. So this difference between the relaxation pressure and the constant pressure I'm trying to hold for this utterance is going to come in the form of expiratory pressure on the system. There's going to be a lot of pressure on the system to push air out of my lungs just by default by that relaxation pressure or force. That will continue until the relaxation pressure becomes less than the constant pressure I'm trying to hold for this utterance. So it's going to switch over here conveniently at the sort of the 50% mark. And then at that point, because the relaxation pressure is less than the constant pressure, there's actually going to be inspiratory pressure because of the difference between the two. So the relaxation pressure is going to be less than the pressure I need to maintain the utterance. And so basically my body is going to want to inspire or breathe in to sort of make this happen rather than the opposite. So and then of course, I'll point out here too, that once you get to the far end of this curve, this becomes exponential as well. It's hard to, when you really compress your lungs, to keep compressing them. You have to put more and more effort into that to counteract the relaxation pressure that wants your lungs to go back to that equilibrium. So this becomes bigger and bigger as we go towards the tail end of the curve. Okay, so relaxation pressure is going to change from expiratory here to inspiratory. So once you get past that equilibrium, which is a little bit higher here because we're keeping the airflow out of our lungs constant, the lungs are going to want to sort of go back to being bigger. Here they want to be dramatically smaller. Here they want to be bigger. Here they want to be dramatically bigger. So relaxation pressure changes from expiratory to inspiratory when you go from the maximum to minimum vital capacity. Okay, I've tried to walk you through that in as great as detail as possible. I know it might be mind-numbingly boring, but it's still true. Okay, so what you have to do to sort of keep that alveolar pressure constant is that you have to counteract this relaxation pressure, these shaded areas on either side of this equilibrium that you're trying to maintain. So when your lungs really want to contract, you have to really actively keep pushing them out. So we're going to be constantly breathing out here, but at the start, we're going to be actively breathing in or using the muscles that we normally use to actively breathe in. So our effort is initially going to require inspiration, or those muscles that normally inspire or make the volume of your lungs bigger, just to kind of counterbalance that effect of the relaxation pressure. And then once we get past that equilibrium, eventually we're going to have to kick in the expiratory muscles to keep the flow of air going at that constant rate. So this is usually the analogy I use for this. Hopefully it's clear, but if it's not, I'll give you this analogy such that, like, say you're at the top of a hill, like there's sort of a road going over two hills like this, and you have a car at the top of this hill, and you want to go basically down to the bottom of the valley and then back up to the top of the other hill at a constant speed. So you wind up with your car here. And then what you do is you want to go forward at a constant rate. So you can, if you want, just like release the brake pedal and let gravity do its thing. But gravity will kick in, right, going to the bottom of the hill and keep you going faster and faster. It'll help accelerate you. That's the way gravity works. So instead of letting gravity just do its thing, you will press the brake pedal a little bit, right? So you start going down the hill slowly, but at a constant rate. And then eventually you'll get kind of to the bottom there, and maybe you'll ease off the brake pedal until you get to that bottom point. But after that bottom point, to keep going at a constant rate of speed, you're going to have to press the accelerator, right, to get up the other hill eventually to counteract the effect of gravity. So at the start, using your brake. At the end, you're using your accelerator pedal. The goal is to simply be moving at a constant speed. The way your respiratory system works, going from the high end of your vital capacity to the lowest end, is similar, right? Even if you're breathing out constantly, at the start you breathe in, just sort of like even if you're going forward, you're using your brake pedal. And at the end, you're going forward by using the accelerator, and you're also breathing out by actively breathing out. Okay. So hopefully that makes sense. The way we can actually document that this works is a little gross, a little bit painful, but it is science, so we have to make sacrifices, right, kids? Okay, so we can use this technique known as electromyography, which is normally abbreviated with EMG. And the way this works is kind of exactly the way you think based on this diagram. So it's a little needle with an electrode in it, and you just poke it into one of your muscles like this. And so because it has an electrode in it, and when your muscles contract, there's a little electrical signal that your nervous system sends through it to activate or contract the muscle. And the electrode can register that. And then you link this up to some other system that can record basically the spike of a contraction in your muscles, and then you know what the muscles were doing at any particular moment in time. So the electrical signal is technically known as an action potential. I should have walked through these notes as I was saying that. Basically, what you're going to do is record the voltage and timing of that discharge, which is kind of cool. This does hurt a little bit, apparently. I've never had it done to myself, but apparently it's not that much. So this is a sacrifice that surely we would be willing to make if we needed to. Because what's more important than knowing how things work? Okay, so like I said, if you're trying to do this experiment where you keep a constant flow of air coming out of your lungs, what the EMG data says, and yes, I guess somehow they were able to do this by sticking electrodes into people's diaphragms and these other various muscles as they speak. But when you do this, you are kicking in your inspiratory muscles first, like your diaphragm and your external intercostals. Like I said, the diaphragm is the big mover for breathing in. So that one is only involved at the start, where we're at this sort of exponential phase of relaxation pressure. And once we get into the more linear phase, then we only need to work with the intercostals, which kind of fine tune the airflow. We get past equilibrium, and then the expiratory muscles start to kick in. So your internal intercostals first, then bigger sets of muscles like your abdominal muscles, the oblique muscles, and then your latissimus dorsi, which is one I didn't mention in the earlier diagram, but that is an expiratory muscle too. And so more and more of those kick in to kind of counteract the eventual exponential curve here of relaxation pressure. But we're breathing out constantly. We're using all the various sets of muscles we have to breathe, both inspiratory and expiratory. Okay, and we know that from EMG studies done way back in the day, like in the 50s, I think. Okay, so that's basically how the system works. We can now think a little bit about how this might relate to language. So one way that breathing affects how you speak, or the acoustics of how you speak, is that the intensity of an utterance is primarily determined by alveolar pressure. So hopefully this isn't too hard to understand, but the more pressure inside your lungs, the faster air is going to flow out, the more intensity you get when you're speaking. So this is, again, looking at sort of the air pressure in the outside world. This is the alveolar pressure for, say, a soft utterance or a not so loud utterance. 2 is somewhere in the middle. There's more of a distinction between the outside air pressure and the alveolar pressure. And 3 is for a really loud utterance. which is normally how I speak in class. And I am speaking a little bit louder than normal even when I'm recording this. But basically what I'm doing is I'm creating more alveolar pressure if I want to speak loudly. Turns out, if you do the math and all the other work involved, then doubling alveolar pressure increases intensity by about 9 to 12 decibels, which is kind of cool. So basically you can think about this though in terms of louder utterances needing a greater difference between alveolar and external air pressures to get that intensity. Therefore, louder utterances are going to require more active expiratory force. As I said before, just biologically speaking, our systems want to be as lazy as possible. So we're normally not going to put more effort into it unless it's really important. So maybe that's one reason why louder things, which become more prominent, may be perceived as more sort of crucial to the conversation when a listener hears it, where our attention is drawn to that for whatever reason the speaker has in mind. Okay, when we actually do speak, the way we breathe is a little bit different from how I've been presenting it so far. We have slightly different demands on the system that we make than either normal breathing or the production of a continuous flow of air for whatever reason. So for instance, a normal breath cycle will last about 5 seconds. You can think about that. There's 60 seconds in a minute, right? So that means you breathe about 12 times per minute. Quick math, I think that means you do like 720 breaths per hour, and I can't quite off the top of my head do the math for how many times you breathe during a day, but it's over 15,000 or so. So that's a lot of breaths when you think about it. And each one is crucially important. But 40% of that cycle is going to be devoted to breathing in, and then 60% of the cycle is devoted to expiration. And again, this is a nice little asymmetry because we're actively breathing in, right? And most of the time when we breathe out, we're not putting any effort into it. So we're actually spending more time not putting effort into the system than we are putting effort into it. So that's a win. In speech, that is even more of a dramatic asymmetry because you only have 10% of the cycle, at least time-wise, devoted to breathing in, and then 90% of the cycle is devoted to breathing out or talking. But as you know, when we breathe out, we're putting effort into it in a different way by moving our articulators in all sorts of directions to make speech. So there is going to be an additional effort here, but it's not going to be based that much on the effort we're putting into breathing out because we can take advantage of that relaxation pressure. However, there's a little bit more going on than that. So normally breathing will encompass about 35 to 45% of vital capacity and will end above the resting expiratory level. When you speak, normally in a conversation, that will encompass a little bit more of that range from 35% to 60% of your vital capacity. Again, staying on top of the resting expiratory level, which is at about 35%, but maybe going a little bit higher in case you want to speak a little more loudly. Loud speech, however, will usually start higher than that at about 60% of vital capacity and go up to like 80%, and may end considerably above the resting expiratory level. So you're just shifting the whole range upwards to get more intensity out so that other people can really hear what you have to say because it's that important. Okay, however, normally in breathing or speech, you don't use the extremes of your vital capacity because it gets kind of exponential at the ends of the range. It just becomes less efficient to use those parts of the system. And you don't want to use that much muscular effort unless you really, really have to, which is rare. Okay, so you can think about this. This is from that chapter in that book from a long time ago that I based these lecture notes on. It gives you some idealized graphs of how your lung volume changes as you're breathing. This is sort of the curve you expect to get for what they call tidal breathing, which is just normal, the normal breath cycle. So you increase the volume and then it decreases through relaxation pressure, and then you increase it again through a nice sort of sine wavy pattern, which is nice and pretty to look at. This is the equilibrium level here. This is the sustained tone, this kind of weird example that I walked us all through here. So you increase the volume a lot and then try to make it decrease at a constant rate all the way throughout. We don't really need to care about this because it's not a normal thing to do. What we do or may care about more is what we do with speech, where we increase the volume really quickly. And then as it goes down, as the relaxation pressure contracts everything, we make these minor adjustments to the flow of air coming out of our mouths. That's how we get sort of the variations in airflow that are meaningful in speech, right? So there are frequent demands for rapid changes in muscular pressure or alveolar pressure during conversational speech. And primarily where they kick in is when you get differences between stressed and unstressed syllables. So stressed syllables, again, are going to be more prominent than the unstressed syllables. And the way you make these changes on a quick sort of fine-tuned basis, like I said before, those are made by the internal intercostal muscles. So the muscles lining the insides of your rib cage can make those fine-tuned adjustments that we use for speech. So those are the ones we really have to kind of care about most when we think about speaking and the muscles required to do so. So to kind of wrap this up, I'm going to give you some data which I was fortunate enough to collect through a friend of mine who was doing a postdoc in physics a few years ago. And he was looking at new ways to measure brain activity in fMRI. So maybe you've had an MRI before to look at some sort of structure in your body or your brain or what have you. And that's just this big magnet that you can lie down into and get kind of freaked out because it's kind of claustrophobic in there. But the magnet can create imagery of the insides of your body. And then there's also a technique known as fMRI, or functional magnetic resonance imaging, which can track basically the blood oxygen level in your brain to find out where blood is being directed to when you think about something or do some sort of activity, to see what kind of regions of your brain get involved when you're doing whatever it is the researcher is interested in studying, which is kind of cool. So my researcher friend, so this is based on oxygen levels in your brain. Oxygen gets into your system through breathing. And he was doing this study, which I don't know exactly all the details of, but it involved changing the amount of oxygen that was going into your system. And he needed sort of guinea pigs to sort of calibrate his system, so I volunteered. So the way he was changing the amount of oxygen that you get into your system is he put basically like a scuba mask on his subjects. So I don't know if you've ever done that either, or if you've done an MRI at all. An MRI is just generally not that much fun for anybody. But then also, I never had a scuba mask on, and I found out that's not much fun either, because you really have to kind of put effort into it just to get air into your lungs. So that's a little claustrophobic as well, or freaky as well. So I went into this, and I didn't really like being in the MRI. I'm happy to do it for a friend. And I didn't really like having to breathe using a scuba mask while I was in the MRI. It was kind of a double whammy. But hey, I got data out of it, so that was a sacrifice I made for science. And so he was looking at how much carbon dioxide he put in the flow of air through the scuba mask and how that would affect the amount of oxygen in my brain. So, I was slowly being suffocated to death. The main thing is that I did not die, and then also the experiment kind of crashed because the system that was collecting data from the MRI wasn't working. But the system that was collecting data from the mask, which was measuring oxygen and carbon dioxide levels in my breathing, was working fine. So I did get this data, which shows you air pressure changes as I'm breathing in and out here during normal breathing. It's not actually sine wavy. It actually amazingly kind of looks a lot more like the sort of waveforms we normally get for phonation at our vocal folds, because it's kind of pointing at both the top and the bottom, which is kind of cool. What's more cool or more complicated is what happens when I'm speaking. So this is looking at pressure changes in the outside system. So this is when I breathe in. And then these are the fine-grained adjustments that happen when I breathe out. So it doesn't kind of like consistently go down to here. I kind of just like plateau and then make lots of rapid changes. Then I need to breathe in again really quickly. So there's less pressure in the outside world, more pressure in my lungs, and then it comes back and I breathe out. So that's what happens when the air gets sucked in, is that all of a sudden it's flowing in, do this pressure change, and then I get kind of the same thing over time. This is the system he had measuring carbon dioxide. So this is me sort of breathing in. And then I'm breathing out here as I speak. So more and more carbon dioxide gets out into the mask until it reaches a sort of crucial point. And then I breathe in again, and then I have to sort of repeat the whole cycle. And you can look at this on the next slide, maybe. Come on. There we go. This is the fine-grained look at what's happening when I speak. So lots of little changes here as I speak. They mean something to us when we look at them in waveform form. At this level, it's hard to get anything out of them. And then these are the quick breaths I have in between each spoken utterance, which is kind of cool. So like I said, very little time is devoted to breathing in when you speak. A lot of time is devoted to breathing out. I think you kind of knew that already. And I've talked a lot in this lecture, so I'm not going to talk a whole lot more. I will keep breathing no matter whether I'm speaking or not, at least for the time being. And I can give you this one last note before I say goodbye, which is that when you have higher airflow coming out of your lungs, you not only increase intensity, but you increase F0. So in the Course of Phonetics textbook, they talk about this bit. I'm going to take a drink here. As an experiment you can do to kind of verify this for yourself, stand against a wall and then try to do that experiment. Hopefully you can see me all right. Try to do that experiment where you're constantly breathing out. It's like, yeah, okay. When you push your stomach, so in the Course of Phonetics textbook, it says you should, have a friend do this for you so it's unexpected. It works either way, and maybe it's less dangerous if you're doing it to yourself. Could be fun though if you get somebody else involved. I don't know. Could be terrible maybe as well. But basically, try to breathe out constantly and then push your stomach in so that you push more air out of your lungs. And you should hear intensity go up and F0 go up as well. Okay, yeah. There you go. Hopefully that's not too complicated to figure out. And it may as well be a bit enjoyable, at least for somebody watching at home. Okay, so increased F0 is also a contributor to stress. So basically more airflow coming out of your lungs is going to increase the prominence of whatever you're speaking or producing in speech. So that, if you're putting more effort into it as a speaker and the listener is more likely to notice it, you can kind of get a payoff for the extra energy you have to contribute to speech. And that's why we do it. So we only use it for important things or the most important things, usually speaking. And that's all I'm going to say about breathing and how we use breathing in speech for now. I think we answered our 3 questions from the beginning. Next time, we're going to talk about how we normally, or more importantly, tweak F0 levels in speech, which is by using different activities of the larynx and the muscles that control the ligaments that form the interesting structure and important structures of the larynx. That's a lot of words to say that we're done with breathing now. Normally, the way you affect F0 levels in your speech is by changing different parameters of what's going on behind the scenes here. So we'll find out about those next time. It's pretty fascinating and also fun in its own way. So I hope you join me, and I'm going to stop talking now. See you then.